So what is a rational function? We saw yesterday that when finding the roots of a polynomial, we can use long division. This is kind of our last resort in finding roots and factoring polynomials. And it's best if we're given the roots. There's some other theorems called the rational root theorem and Descartes' rule of sign and all sorts of extra tricks that we're kind of skipping over that can help you find the roots of polynomials. The problem is ultimately it does come down to a guess and check process where you just have to guess and check these roots and do either long division or synthetic division. And what we realize is in checking these roots, it is equivalent to dividing polynomials. And when we divide polynomials, as we kind of saw that, sometimes we get a remainder term. What is the remainder? The remainder is essentially telling us that we cannot write a division of polynomials as another polynomial. In other words, we can add, subtract, and multiply polynomials, and we still get polynomials. However, as soon as we start to divide, we're not necessarily getting polynomials anymore. We need a broader class of functions, and that class of functions is rational functions. And this is kind of how we're building it up. So far, we've kind of had a nested sequence where we start off with lines. Those are degree 1 polynomials. Degree 2 polynomials are our quadratics. Then we did general polynomials, which cover all of those. Lines are degree 1, quadratics degree 2, fit inside our bigger class of polynomials. And now rational functions actually contain polynomials. Polynomials are technically rational functions as well, just with a denominator of 1. So let's formally write that out. A rational function f is a function of the form f of x equals p of x over q of x, where p of x and q of x are polynomials. And that's really all there is to the definition. Let's try to get to a couple of examples. And our first goal, anytime we have a new class of functions, is we want to understand how these graphs, we want to be able to see the shape of the functions, and are there any special points that we should be looking out for. So far with our polynomials, we determined end behavior, and our special points are our intercepts, are the most important points and information we can pick off of those graphs at a pre-calc level. Let's do the same for rational functions, but before we get there, let's do one example. Let's kind of sort of just finish up our process and go over that one more time with polynomials. So the example is just graph f of x is negative 1 over 50 x minus 1 times x minus 5 squared times x plus 2 cubed. And actually, let's add on one more factor just to illustrate a point that we need to talk about. Let's say x squared plus 1, and let's say that itself is squared. So this is a pretty long polynomial, really complicated, really technical. However, it's written in kind of a nice form. This is our factored form. So what were our steps for graphing? Let's just go over those one more time. Our first step was to plot the end behavior. The x and y intercepts. We then plotted the root behavior. Those were all of our signs. There are all these little tick marks or U marks, whether we're crossing or bouncing off of the x-axis. And then our last one was to just connect everything. Sorry, let me pause the video real quick. Okay. So let's go ahead and talk about each of these pieces, since we didn't do an example like this on Wednesday. On Wednesday, we were working with primarily factoring polynomials and actually getting our polynomial into such a form. So that way we could figure out the roots and then figure out the root behavior and everything from it. But if we have a really large degree polynomial, so if we have degree 3 and 4, we saw some tricks yesterday where we can factor it, and sometimes we're given information about the factors that can then help us reduce our polynomial down to degree 2 factors. And if we're in degree 2 factors, we're good. We know all of our factoring techniques from those and even have the quadratic formula. But this is a very large degree polynomial. And when we get really high degrees, the best thing to do, or the only way we can really ask those problems, is if it's already pre-factored for us. Because if this were an expanded form, the time it would take us to pull out each of these factors would be, it'd be enormous. And it wouldn't be a good quiz problem, wouldn't be a good test problem. Maybe something like that appears on your homework, but I wouldn't expect something more than a degree 5, something where you would have time to sit around and work out. So we've got our steps in order, but I'm actually going to say 1 and 2 we can kind of do interchangeably. And it kind of depends on how the function is given, right? Our 1 and 2, we're really just plotting these tick marks and our points on our intercepts, and they don't really interfere with each other. We need those two before we move on to the next 2 steps, but these two, doesn't quite matter which one we do in order. And actually, since we have it in factored form, I'm going to go ahead and do the x and y intercepts first. If it's in expanded form, the end behavior is almost always easiest to do first because you can immediately read it off by the leading coefficient and the degree of the polynomial, right? That's what we're looking for end behavior. But in factored form, what can we almost immediately read off are the x-intercepts. So let's go ahead and start with that. The y-intercepts will take us a little bit of work, so I just want to go through all of these steps now and how they kind of change when we're given the function in a different form, and how to be careful about keeping track of all the information that's in this polynomial. So let's go ahead and start number 2. And nicely enough, when it's factored, we would just take each of the factors and set it equal to 0. And the thing, hopefully everyone's noticing, that, well, if the factor itself has a multiplicity, multiplicity doesn't matter. It's not going to change the actual solution. And so instead of going through all these, I'm just going to go ahead and write them down. And hopefully you can see that those are the first 3 roots. The last one, if we wanted to check ourselves, and I added this one in there specifically because an x squared plus 1 equal to 0. When we try to solve this, we would get x squared is minus 1, and if we take a square root, we get imaginary numbers. So no extra roots from this factor. Essentially what that factor is going to do when there's imaginary roots, it is going to increase the degree of the polynomial because we're multiplying by more powers of x. And then the other thing it can do is maybe adjust the y-intercept. And I'll show you how to get the y-intercept here just in a second. The other thing it's really going to do graphically, which we can't really plot in our graph, is because we're increasing the degree, it's just going to make everything a bit steeper. It's going to be sharper ups and sharper downs and decrease and increase faster at the endpoints, at the rates of infinity. But that information we can't really graph accurately at a pre-calc level. So it's not, it really doesn't affect the graph too much in terms of if I had just left that factor off and left us with this factor. So our y-intercept, we actually have to do a little bit of work for. When the polynomial is in expanded form and it's just, an, x to the n, and they decrease in order, the y-intercept is always the constant term. It's always that last value plus whatever constant at the end. And so the nice thing about expanded form Well, we have our lead coefficient and can determine end behavior, and we can also determine the y-intercept very easily, do work for our x-intercepts. If it's already factored, that kind of simplicity switches, essentially. The x-intercepts are easiest to find. We have to do a little bit of work for the y-intercept, but not a whole lot. So how do we find the y-intercept? Well, we just plug in x equals 0. We kind of have to do it the old-fashioned way, but luckily, it's not too bad. So we've got our minus 1 over 50 out front, and when we're plugging in x equals 0, it's going to make all of these expressions pretty simple. There's no real calculation in determining what goes in each of these parentheses when x is 0. We're essentially just reading off those constants, and all we have to do is now multiply them all together. But we also have to take into account the exponent, so multiplication with the exponent involved, and we also have to pay attention to the constant out front, our negative 1 over 50. So how do you do multiplication? Let's go ahead and keep that 50 in the denominator. Let's determine plus or minus just so we get the signs right. So that's a negative, that'll be positive. I have negative 5, but that's going to be squared, so that'll be another positive. We essentially have 4 negatives being multiplied, 1, 2, 3, 4, and that'll overall be positive, so I'm not even going to worry about the sign. And then what's going to happen when I multiply these numbers together? 1 and 1 aren't going to affect anything. 5 squared will give me 25 times 2 cubed gives us 8. Trick when multiplying things by hand and doing your scratch work, don't multiply everything all out.
I think I'm going to send him a private message.
If it's multiplied as a factor, or if it's already multiplied in factors as a number, keep it like that, and then try to factor the other terms as well. So let's factor the denominator, just so, right, 25 times 8, not too bad of multiplication, but we can even save ourselves some time just by factoring 50. 25s cancel, 8 divided by 2, and we'll get 4. So let's go ahead and plot this. 1, 2, 3, 4, 5, 1, 2. We've got 1, negative 2, and 5. And then we've got our y-intercept of 4. And now let's figure out the end behavior. And this is something you got to be a little careful on. Because it's in factored form, determining the degree can be a little difficult. So one thing to note, all of those coefficients are 1. We saw an example yesterday where I had a factor of 2x minus 3. And we showed how you can manipulate that into x minus a to a power, x minus a to a power. We like that kind of form because it immediately tells us what the root is, and these coefficients are all 1. And when it's like that, the constant out front will become our lead coefficient. So determining our end behavior, we need to know our degree and our lead coefficient. But if I'm given it in factored form, we do not want to expand this thing. It's a lot of work to multiply everything out. So what we have to do is try to think of some shortcuts and ask ourselves, what would happen if we did expand everything out? So let me just talk through that real quick. We only have 1 power of x here. Our lead coefficient, so what I'm doing is counting the highest powers of x and seeing what would happen if I multiply them together. Here I just have 1 power of an x. If I multiplied this term out, it would be an x squared. But that x squared times x still just gives me x cubed. And the coefficient still is just 1. Likewise with all these other factors. Here I would have an x cubed, times these other x cubes after I expanded that whole guy out. That would give me an x to the 6th lead coefficient of 1. And then what's this term going to do? You've got to be careful with this too. It's an x squared plus 1, and then when I square it, it'll be an x squared squared, giving me an x to the 4th. So that, and then times everything else, which was an x to the 6th, will give me an x to the 10th with a lead coefficient of 1. Then times this constant that's being out front, our lead coefficient remains what this is, this minus 1 over 50. So that told us two things. Our degree was 10, and our lead coefficient is minus 1 over 50. So degree, you have to just remember to count the powers of x. So 1 plus 2 more powers of x plus 3 more powers of x plus 4 more powers of x from that guy. Gives us a total of 10 powers of x, or an x to the 10th gave us that degree. So it's an even degree, negative lead coefficient, meaning our end behavior is going to be both downward. And now we just have to plot the root behavior. So our 2 was a cubic, which means it's going to cross. If you want to be fancy, you can cross like a cubic would and make it like a little loop. If you want to just put a dashed line, perfectly fine as well. At 1, it's a degree 1 multiplicity. So we're going to cross again. And then our 5 was degree 2. So we'll bounce. And here, let's make this guy a little steeper, still crossing. And now what we got to do is connect the dots. So we'll look something like that. Come up, around, down, come down, and then connect that out. Any questions?